Okay, so now that we've handled a little bit of the energy end of things in this chapter 2 on energy and matter, let's start to change our focus to matter and look at how we define matter and then how we classify matter. So as we look into the classification of matter, we're going to try to think about big categories of matter so that we can have things lumped into just a couple of categories instead of subdivided into very, very small and defined groups of matter. Let's take care of the big stuff first. As a reminder, if it's been a while since you've talked about matter, the definition of matter is anything that has mass and occupies space, or has volume is another way to say that, occupies space. It's not much better than that vague definition of energy is the ability to do work, but it's something, okay? So if it's matter, it's stuff. It has mass, it can be weighed even if it's a very, very small mass, and it occupies some three-dimensional volume. Matter makes up everything we see every day, such as water, wood, cooking pans, clothes, and shoes. Again, if it's not energy and it's something in the universe, it's matter. And of course, energy and matter have that duality that we may touch on later, but the sort of Einsteinian physics that when we get into what's called quantum mechanics, things get really strange. But let's keep it simple here, and we'll define matter as a pure substance or a mixture. So that's matter's the big concept, and all the matter in the universe is going to nicely fit into either this category of pure substance or mixture. Well, what do we mean by pure substances? Well, a pure substance has a fixed or a constant composition, and as such it can be classified as either an element, which again there's about 118 of those known, and most of them that have been discovered recently don't exist for very long, or a compound, and many, many more substances are compounds than elements. So 118 elements, but billions upon billions of possible compounds by combining them. And if we look at elements themselves, they have just one type of atom. So one of those 118 atom types out there, an element would consist of just one of those types. And then a compound has two or more elements chemically combined. So think of table salt or table sugar or sand, all these common things that we encounter in the universe. They're typically compounds. Very few elements exist naturally as elements. Gold, you might be lucky enough to find a vein of gold in the earth, or certainly the oxygen and nitrogen in the air. Those are some examples of some elements, but it's much more likely that you're going to encounter something as a compound than as an element if you're dealing with a pure substance. Alright, so again, to be very clear about this, elements are pure substances that contain atoms of only one type. So some examples would be copper. Again, the penny's not a great example. The outside is copper, but the inside is zinc. So there's actually two elements involved there. Lead is mainly pure lead, and that's one that does exist in nature and has been known, like copper, since ancient times, which is one reason those copper and lead symbols seem a little strange. Copper, there's no U in the English word copper. The Cu symbol comes from cuprum, which ultimately comes from the island of Cyprus, because that's where copper was abundant in the ancient world. Lead, neither a P nor a B in lead, but it comes from plumbum, which is the Latin name for it, and sort of onomatopoetic term for if you drop lead, it makes sort of a plumbum sound. And plumber is a profession today that they don't deal with a whole lot of lead because we know better than that now. It's not a very safe element to be using for pipes because it does leach a little bit, and over time that exposure to lead can be dangerous. But since it's been known since the ancient times, it also has an element symbol that's based on the Latin name. Finally, aluminum, which has been discovered much more recently as a pure element. Actually, just over 100 years ago, pure aluminum would be worth almost as much as gold, weight per weight, because it was very tough to prepare. And then we found electrochemically how to make it very cheaply, and nowadays we just toss away aluminum foil when, like I said, 100 years ago, that aluminum might be better served as a crown for royalty. Okay, so again, the elements, there's 118 known elements, and these elements very rarely exist as elements in nature, but can be synthesized by humans, made into elemental metals like aluminum, even though they wouldn't exist in nature as such. So if we look into compounds now, of course, compounds have two or more elements that are chemically combined in some definite ratio. An example is things we already talked about, table salt, sodium chloride. You have the element sodium and the element chlorine come together, swap electrons, and become the ions sodium and chloride. You have table sugar, which is a molecular substance based on carbon, hydrogen, and oxygen atoms. So those three different types of atoms present in that sucrose molecule. And then many, many sucrose molecules in each grain of table sugar. And finally, water, which even our hero, Antoine Lavoisier, the father of modern chemistry, he thought that was an element because it was so difficult to separate. He thought it was indeed an element, but we know now that it's a mixture. It's a compound made of two atoms of hydrogen chemically combined, covalently bonded to one atom of oxygen. So again, these are just a few examples of the billions upon billions of compounds, much more diversity among compounds than among elements, because these compounds can be made of some mixture of elements in any number of ways. So table sugar itself, there's that sucrose, we also have glucose and fructose, and just combining carbon, hydrogen, and oxygen, we have millions and millions of different possibilities. So although we tend to classify matter as either an element or a compound if we're talking about a pure substance, we can convert between the two. That involves chemistry. We can't just physically change one to the other, but we can chemically convert. So table salt's a compound that contains the elements sodium and chlorine, and if we were to electrochemically treat sodium chloride, we could force those ions to go back to the atoms, and we could reform sodium metal and chlorine gas if we had the right conditions. Likewise, if we bring sodium metal and chlorine gas together, then they will generate sodium chloride in a chemical reaction, a very energetic reaction. Substances that would be toxic to us on their own, sodium metal is toxic to humans, chlorine gas toxic to humans. Combine them together and you get something relatively harmless. Again, if you take in too much sodium chloride over too long a time, or too much at once, if you really overdo it, right? Just like Paracelsus said, the dose makes the poison. You could find yourself a victim of sodium chloride overdose, but that would take an awful lot of sodium chloride compared with the amounts of sodium metal or chlorine gas that would be involved. Alright, so if a pure substance is either an element or a compound, let's talk about mixtures. Mixtures are even more likely the way you encounter matter in the universe. A mixture is matter that consists of two or more substances that are physically mixed, not chemically combined. So not like combining elements into a compound, but rather just taking two compounds or two elements or an element in a compound and mixing them together. That often can lead to a composition that is not constant, although sometimes it gets a fairly constant composition. If you go down to the atomic scale, it's possible to separate the different components of the mixture. And finally, the separation can be separated by physical methods. So we think about salt water, for instance. That's two compounds, water and sodium chloride. As we combine them, the sodium chloride ions dissolve into the water molecules surround them, and it looks just like plain water, but certainly tastes different and behaves different in terms of its melting point and boiling point. So the way that you could separate them physically, you could heat them up and you'd drive the water off and you'd reform the sodium chloride crystals. So if we want to think about that physical separation for a little easier to picture system, again, with only physical changes, we could easily separate pasta and water by using a strainer, right? The strainer is going to allow the water molecules to pass through, but the large winding pasta would not be able to pass through the strainer. So therefore, we can separate that mixture of pasta and water by using a physical strainer, which has holes that are too small for the pasta to flow through, but large enough for the water to flow. When we think about these techniques in a laboratory setting, we tend to think about physically separating mixture by either filtration or by chromatography. So in the left image there, we see a solution that has a suspension, really, something that it looks like a solution, but it's not a true solution. The particles are small, but not really mixed at the molecular level. So if you use filter paper, you can let the water flow through, and we see the water is coming through nice and clear and colorless, and we're leaving behind that yellow suspension. Those suspended particles are now trapped by the filter paper. The filter paper won't allow those through. It allows the water through, and we can physically separate by filtration. That's called gravity filtration, that method being demonstrated. There's also chromatography, and that's an example of paper chromatography on the right, where we have some chromatography paper, and we took a black marker, for instance, and we allowed a solvent to climb up the filter paper and to separate that black marker, those inks, into their component colors. And again, chromatography can happen in the gas, liquid, or solid phase. This happens to be a solid support, the filter paper itself, to separate the dyes in something like a black marker. Now, just like we define pure substances as either elements or compounds, we can classify mixtures by their composition, and they tend to be called either homogeneous mixtures if they're uniform throughout, and we'll see those. We also know as solutions. And then finally, heterogeneous mixtures are not uniform throughout. Depending on where you are in the sample, you're going to get a very different profile compared with a homogeneous mixture that, at least at the macro scale, should be the same throughout. Okay, so again, homogeneous mixtures, also known as solutions, they're characterized by constant composition, a uniform composition throughout the material, and different parts of the mixture are not visible, so we see it all at once. Here's an example of a brass urn, and brass is a solid solution of copper and zinc. So the copper and zinc look different when they've been combined. Brass is a nice shiny golden color. It's not copper colored. It's not, zinc would be a silvery metal color. It's neither of them. It's this blend that gives you that brass color that's very nice, shiny, almost golden appearance. So things are different, and those copper and zinc atoms are mixed at a molecular level. So you're not getting a copper on top and a zinc on the bottom. You're getting copper and zinc mixed thoroughly throughout. If we consider instead a homogeneous mixture, here the composition is not uniform. It differs from place to place within the mixture, and different parts of the mixture are clearly visible. In this case here, with the water and the copper, right at the naked eye, you can see the copper is down below, the water is up above. They're in contact at the interface, but if you were to just sample at the top of that mixture, you'd only get water. If you were to sample at the bottom, you'd only get copper. Only if you sample at the interface would you get a mix of the two, whereas in the case of a homogeneous mixture, you always get that constant composition no matter where you sample at the macro scale. Alright, so now that we have filled in a little more, we have a new graphic here where we have matter, that big idea of stuff, anything with mass and volume, being classified as either pure substances or mixtures. And then as we move down, if we go down from pure substances, we get either elements or compounds being possibilities. With mixtures, we get either homogeneous mixtures or heterogeneous mixtures. And therefore, now hopefully you have a better sense of classification of matter into elements, compounds, and the two different types of mixtures that we've discussed so far. Okay, so let's test our knowledge here by a couple of learning checks. First, in this learning check, let's identify each of the following as a pure substance or a mixture. So A, pasta and tomato sauce, B, aluminum foil, C, helium, and D, air. So for each of those, just decide whether it's a pure substance or a mixture. Jot down your response. Pause the video if you need another moment. Otherwise, we'll see how you did. Okay, so pasta and tomato sauce, obviously very different if you're getting just the pasta or just the tomato sauce versus getting a nice blended area with both. So that's an example of a mixture, two different substances physically combined. B, aluminum foil, is a pure substance, and if you want to go even further, it's an element. C, helium, another example of a pure substance, and in this case another example of an element. And finally, D, air. Air is a mixture of mostly nitrogen, elemental nitrogen, N2, about 78%, about 21% oxygen, O2, and then aside from those elements, you've got some of the other noble gas elements present in some small amounts, neon, argon, those sorts of things, as well as certainly a number of compounds, carbon dioxide, hopefully not too much carbon monoxide, but other things like that are possible components of a mixture of air. So hopefully that last learning check was nice and easy. Here's another one that I don't think will pose too many problems. So go ahead and identify each of the following as a homogeneous or a heterogeneous mixture. So these are all mixtures. We're just concerned with, are they homogeneous, same throughout, a true solution, or are they heterogeneous, different composition throughout? So A, a hot fudge sundae. B, a clear, colorless shampoo. C, sugar water. And D, peach pie. So for each of those, identify each as either homogeneous or heterogeneous mixture. Pause the video now if you need another moment. Otherwise, we'll check and see how you did. Okay, so here we are. A hot fudge sundae is a heterogeneous mixture. You might get some fudge in the very top, or maybe some fudge and some ice cream further down, and maybe just ice cream by the bottom. So heterogeneous mixture depends on where you sample, especially if you have a cherry on top. That cherry is not going to be throughout the sample, just at the very top usually. If there's a clear colorless shampoo, that's a homogeneous mixture. It looks like one thing throughout. The surfactant molecules are mixed in there with the water and the other components of the shampoo. So that's an example of a solution, also known as a homogeneous mixture. Sugar water, same thing. It doesn't matter as long as you've mixed up the sugar in the water and it looks just like plain water, whether you take a teaspoon sample up at the top or you use a straw to get a sample from the bottom, it should taste the same throughout. It should have the same amount of sugar throughout because it should be a homogeneous mixture, a true solution. And then finally, peach pie. That's an example of a heterogeneous mixture. You might have the crust at the top or the bottom. Right in the middle, you get just the peaches. So depending on where you sample, you get a different profile there. So that's, again, a heterogeneous mixture. Hopefully these learning checks were nice and simple, and the homework set questions on these topics hopefully also you find simple. If not, make sure to do some extra work in the text, those end of chapter questions. And if it's still not clicking for you, please don't hesitate to contact me, and I'll do what I can to help clarify these classification of matter concepts.